Welcome to Part 5 of Chemical Equilibrium. This is Dr. Kofelt. In Part 5, we're going to continue our discussion of how we calculate equilibrium concentrations using the equilibrium constant. But this time we're only going to have the initial concentrations or pressures. So before we either had initial and equilibrium, or we had initial and at least one equilibrium concentration. In this case, and then we were able to figure out all the rest of them. In this case, however, we're only going to have an equilibrium constant, the initial concentrations, and that's it. So we don't know what the equilibrium concentration looks like, and we don't know what the change is. And so what we're going to have to do is we're going to have to use X to represent the change. So finding equilibrium when you're given initial concentrations only, you're going to use the ice baby table. All right, so first step is you decide which direction you're going in. You can either use the Q and K, or you can look at it and see what you think. You know, Q is the way to be sure. Define the change, or sometimes the problem will tell you, right? Define the changes of all the materials in terms of X. So you're going to use the coefficient from the chemical equation as a coefficient of X, and still use the stoichiometric ratios, but the increase in material on the product side is going to be plus, and the decrease in materials on the reactant side is going to be negative X. And then you're going to solve for X. And so for second order equations, you're going to use square roots of both sides, or you'll have to use the quadratic formula. So in this section, we're only going to do the square roots, because we're going to have perfect squares in these first examples, and I'll show you how to kind of figure that out. All right, and then you're going to simplify, obviously. Now, we're not doing it yet, but I do want to remind you of the quadratic formula. And the quadratic formula is what you're going to use when it is not a perfect square. And you rearrange it into the ax squared plus bx plus c equals 0. There is a section, if you've got mastering chemistry, there's a tutorial in there about using the quadratic formula to solve for things. And then, of course, you're going to use x equals negative b plus or minus the square root of b squared minus 4ac, and then all of that over to a, if you remember the song, you can say it in your head. Okay, so but for now, what we're going to do is we're going to hopefully use these that are perfect squares. So you have to make sure you keep the signs with the B and the C part of that equation. Also remember, if you do a quadratic, then only one of the value will make sense. One of them will not be possible, the other one will make sense. That is, you can't have a 0 for a product, and you can't have more reactant when you get done than you started with. So those are some clues that you can't have that particular value of X, and one will make total sense. Okay, you just have to look at that, make sure that it makes sense to you. Remember, in chemistry, it's not just about rote memorizing how to do exactly one type of mathematical equation. You have to apply what you learn, and so that's what we're doing. And I'm giving you examples of all these ways that you do ice, but you have to evaluate what information you're being given so that you know which method you're going to be using. So the ice table, if you recall, is initial concentration, then the change, and then the equilibrium concentration. And so it just gives you, in this case, we're using X as a variable because we don't know. If we know the initial and the equilibrium, we can figure out what the change is. If we don't know that, then we have to just say, okay, it's going to go down by X, or it'll go up by 2X, depending. And it goes up by 2X because the coefficient is 2, and it goes down X because the coefficient is 1. Okay, I know, sound like gobbledygook first. Okay, hopefully when we work one, it'll make sense. I know if you're like me and you're kinesthetic, you got to work one. Okay, so we look at this first one, and these take a little room. I've got a second slide if I run out of room, but I'm going to try to get it all on here. So I may write a little small, so just bear with me. Maybe you can blow this up or, you know, oh, don't say that. That's not a good thing to say right now. Okay, so first thing we're going to do is I'm going to look at the changes. Okay, so I'm looking at the changes. I have KC at 0.1. It's at 2,000 degrees C, so we're really, really heating this thing up. The N2 is 0.2 molar, and the O2 is 0.2 molar. Okay, and I have one of each of those, and then I have two of the NOs. All right, and obviously when I first start out, I don't have any product, so at least I know what my initial conditions are. Yes, yes. Okay, so since I don't know what the equilibrium is, and it doesn't tell me what the change is, then I'm going to look at this and decide, has it reached equilibrium yet? And so the way I do that is by doing Q. So Q is equal to NO2 squared, sorry, NO, divided by N2 times O2. And those are just to the first power. So when I put this in here, that's 0, right? Divided by 0.2 times 0.2. All right, and so that equals 0. And so the 0 is less than 0.10, so Q is less than K. So that means it's going to the right. So it proceeds as it's written. Okay, so that means that indeed these are the reactants, and that is the product. All right, so I'm going to use X to figure out what's happening in this. So I'm going to say that it's going to go down 1X, and so is this one. But this one will go up 2X. See why I did that? Because it's in molar ratios. So I'm doing them proportionally. So if it's 1 mole to 1 mole to 2, then it'll go down 1, but this one will go up 2. So my equilibrium in terms of X is 0.20 minus X, 0.200 minus X, and 2X, because 0 plus 2X is 2X. So this is my equilibrium concentrations, basically, in terms of X. So I'm going to set Kc, and I'm not going to write this because it's the same, okay, of NO squared divided by N2, O2. So that's going to give me 2X squared divided by 0.2 minus X times 0.20 minus X, which is basically what? 0.2 minus X squared. So it's 2X squared divided by 0.20 minus X squared equals Kc, which was 0.10. Now, oh, happy day. Now, oh, and make sure you don't do what I just did. All right, all right, so this whole thing is squared, okay? So that means that it's literally 2 squared, which is 4x squared divided by 0.200 minus x squared, because the 2x is squared, so you have to square the number as well. All right, so 0.1 is equal to 4x squared divided by 0.2 minus x squared. So and I'm going to rewrite it over here so it's a little bit easier to see. I'm just rewriting that so it'll be kind of in a form. And you'll see why I left them in their little square things. Okay, so if I take the square root of both sides, I'm going to get rid of those squares, because 0.2 minus x squared, I'd have to factor that. And oh my gosh, you remember factoring? that's that thing you thought you'd never use again. We could. You can do it that way if you want to, but you really don't have to if it's a perfect square. All right. So if I take the square root of both sides, then what that gives me is the square root of 0.1 is equal to 2x divided by 0.200 minus x. Okay, and then I can cross multiply because I want to get my x's. I got to cross multiply to get everything situated, and then what I want to do is I want to get combine like terms, as they say in the math world, and get the x's together and the numbers together. So square root of 0.10, and you can do that if you want to. I'll just leave it till the end myself. Times 0.2 minus, because if I'm cross multiplying, now I'm going to have 0.1 x is equal to 2x. All right, so all I did was cross multiply. All right, so once I've done that, then I'm going to do the square root of 0.1 times 0.2, which turns out to be 0.063. All right, and then I'm going to move this over here, so they'll be together. So then the x's will be together. All right, so it'll be over here 2x plus, because this was a minus, so it changes sign, plus the square root of 0.10x. So 0.063 equals, I'm just doing all the steps. So it's 2 plus whatever the square root of 0.1 is times x. So it's 2x plus 0.3x. So that equals 2.3x. I just took that square root of 10 and added that to 2. And that, so now I've combined I've got my x's all together. So now what I can do is I can say, if I want to solve for x, so x is going to be equal to 0.063 divided by 2.3. This is basic algebra. If you need to bone up on it, go to the mastering stuff. Okay, and that gives me 0.027. Now 0.027 is x, okay, and that's going to be in molarity, right? Unless it was atmospheres, but it's in molarity in this case. So, but I'm not done yet because that's x. So now I have to go back and look at my table, right, where I had my x's, and so the concentration of nitrogen, because that's what it's asking me for, it's the concentrations of this stuff, right? Concentration of nitrogen, it's the same as oxygen, okay, because they're 0.2 minus x. So that's going to be 0.200 minus what I found for x, which is 0.027. So that's going to be equal to 0.172 molar. Okay, so that's the concentration of each one of those, because they're the same stoichiometrically. And then to get the concentration of NO, that is 2x. So that's 2 times 0.027. So that's going to be 0.054 molar, which is the concentration of the NO. So that's not too bad because since it's a perfect square, I can take the square root of both sides. As long as you can do the math and don't mess up, right? Always lots of places to mess up in math. And then you figure out what x is, and then you've got to go back to your ICE table. That's why you always have to do an ICE table for these, so that you can see then what the actual concentration is in terms of x. Once you know x, then you just plug that in, but you have to go through this whole rigmarole right here to find out what x is. So, all right, that's fun, isn't it? So this is the second most fun way to do this. And remember, this is when you don't know what the equilibrium is. You don't have any equilibrium concentrations at all, because if you have one, you can figure them out without having to do a lot of high-end math. But if you don't know any of the equilibrium concentrations for sure. Then you have to look at it in terms of X, and then if you're lucky and it turns out to be a perfect square, because this is a square and that is a square, okay, so a square divided by a square, so you can just take the square root of everything and get that calculated. And then I gave you one to try, and this is also a perfect square, okay, so when I give you a practice right after, that means it's the same kind. So this is a perfect square, so it should, if it's not when you first do it, look again, because it should be. And then there's another one. Notice I've underlined and put bold. It's in 2 liters. So I'm giving you moles and liters. So remember what you have to do to get molarity. You have to do the moles divided by how many liters you have to get those initial concentrations to set up your ice table. Otherwise, you're going to mess up. All right. So that is the end of how you calculate using perfect square method, okay, when you're doing initial concentrations, but you don't have any equilibrium.